Welcome back, everybody. This is Unit 12 of AP Chemistry, and we're looking at Section 2, taking a look at how temperatures will be affecting the spontaneity of things. Now, the effect of temperature on spontaneity, there's a couple of different scenarios. If we look at enthalpy and entropy, taking a look at the effects on the energy itself, we see that if we have a negative H and a positive S, that will be always spontaneous at all temperatures. If we have the other scenario of positive H and negative S, we're going to see that it's going to be non-spontaneous, okay? And so you can just look at it. If the question is just asking if this is going to be spontaneous or non-spontaneous, we can answer that question just by looking at it. Now, if we see that we have both positive or both negative, well, then we got to take a look at the scenarios, and this is where temperature comes in. Temperature at a low temperature, it's going to be positive, so that's going to be non-spontaneous. And if it's going to be a negative for both at low temperature, it's going to be the opposite. Okay, so if they have the opposite signs, it's impossible to reverse the direction of spontaneity. And both delta H and the negative T of delta S reinforce one another. So we can do this taking a look at math. And I'm going to actually go back to a problem that we did previously in this first section with the equation of iron 3 oxide with this. And then the reason I'm going to be doing this is just kind of use it as an example. We saw in this equation, we saw that our delta H ended up being 98.8 kilojoules. And we saw that also my delta S was a 0.1415 kilojoules, okay? We did the calculations for that already in the previous section, so I'm just referring to those values. So let's take a look at predicting the spontaneity of things, or the temperature that it becomes zero of this. We're at equilibrium, in other words. So we would set my G value to zero, okay? And so if I remember that if I set my G, my delta G is zero, what that means is that I was zero equals my delta H minus my temperature times my delta S. Okay, my enthalpy and entropy. And so if I bring the delta H to the other side, I would see that my delta H equals my temperature times my delta S. Okay, and then I just substitute my values in, and I would see that I have 98.8 kilojoules. That will equal temperature times the 0.1415. My temperature that this would be at equilibrium would be a 698 Kelvin. Okay, that's where my G value is going to be zero. All right, so that's a pretty easy application of this. And let's take a look at some other scenarios involving the temperature. Okay, at what temperature would this occur? We would just be taking a look at plugging values in and basically just use the equation of my delta H divided by my delta S. Okay, that's all I need to do with that same scenario. Just look up your values and you're good to go. Now let's take a look at how pressure could be affecting this as well. My G value is going to be, that free energy is going to be the change in that times the RT, the natural log of Q. Now remember, when we take a look at this, if I'm using the natural log of Q, the R value is going to be 8.31 times 10 to the negative third, okay? So if you're using the natural log, that's your R value. Now, the Q rules are, if just a reminder, because we calculated these in first semester too. Gases enter as their partial pressures in atmospheres. Got to be in atmospheres. Those aqueous solutions are going to be molar concentrations. And then pure liquids and solids don't appear at all. They're just non-factor. They're just a multiplier of 1. Okay, so let's look at an example of the case of my zinc and hydrogen. Now let's first of all calculate out my G value, okay? So if I do that, my G value is going to be just a factor of, again, I'm looking at my product side first, and so that's going to be just a 1 times the negative, actually, let me get rid of this, my 1 times negative 147.1 plus 1 times 0. Now remember, it's a 0 because it's a gas. That's its natural state. Now we're going to subtract it from my 1 times 0. And the reason this one's a 0 is because I have a solid on my zinc plus a 2 times 0. Okay, and if I just look up the value for this, that ends up being 0 as well. And so I'll end up with my delta G then of negative 147.1 kilojoules per mole. Okay, now let's take a look at letter B then. We're going to be seeing when my G, when I have a partial pressure involved. So that's going to be the delta G plus the RT and then the natural log of Q. Okay, so we already found that my delta G was going to be a negative 147.1 kilojoules. We're going to add that to all of this. Okay, so my R value 0.00831. 8.31 times 10 to the negative third, times my temperature, which was 298, times the natural log of my zinc, and my zinc concentration was a 0.1. I guess I've got a double bracket there. That's okay. 0.1 times my pressure of my hydrogen, and my pressure of my hydrogen was a, let's see, what do I have here? Now this is going to be, oh, here it is, 750 millimeters of mercury. Now be careful, because I have millimeters of mercury, that needs to be in atmospheres. So 760 millimeters of mercury to 1 atmosphere. And that all goes over my zinc, which is a solid, and then my hydrogen concentration. My hydrogen concentration was 1.0 times 10 to the negative 4. Now remember, that's going to be squared. Okay, and so if I do all this math, if I just multiply that all out, I end up with negative 147 plus a 39.9 kilojoules. And so I'll end up with an answer of negative 107.2 kilojoules, and I'm done. Okay, so it really isn't that bad. You just kind of watch how all that calculates out and watch your squares and watch out for those things that are going to be solids or liquids along the way. Okay, so now we want to see if lead chloride, we're going to predict our solubilities based off of this. This is where our solubility tables come in. And so I'm going to have lead chloride is going to, the question is, does it dissociate? So I'm going to be dissociating into this as aqueous. And I'm going to be dissociating into my chloride that's aqueous. And remember, we have 2 of those. Okay, so the question is this going to be spontaneous? All right, when we have those values. Well, in the first case, I see that I have my delta G is going to be, if I just look up values, my lead ion and my chloride ions, I have a 24.4 plus my 2 times negative 131.2. That will be subtract off now my lead chloride, and that's a negative 314.1. That gives me a value of 27.3. So if I plug the values in, my G is going to be that 27.3 minus my constant times my temperature, 298, times the natural log of my 1 to the first power times my 2 to the second power, and that's going to be over 1. Okay, the reason it's over 1 is because that's a solid. And so my G value ends up being a plus 30.71 kilojoules. That means it is non-spontaneous because it's positive. That also means it's non-soluble. Okay, so just kind of looking at those values that way. Not too bad. And let's take a look now if I change the concentrations. I'm going to actually make them quite a bit weaker. Okay, so if I do that, I'm going to use the same delta G value. That's not a problem. So my G is going to be equal to my, what did I have on there? I had plus 27.3 kilojoules minus 0.00831 times my temperature of 298 times the natural log of 1.0 times 10 to the negative 5th to the first power times my 2.0 times 10 to the negative 5th squared. And again, that's going to be over 1. And so I'll end up with my G value is going to be a negative 54.8 kilojoules. All of a sudden, that's spontaneous because my delta G ends up being a negative value. Okay, all of a sudden it did become soluble with it. All right, so just plugging in the values, I don't think you're going to find many problems with that. Just keep track of your equation and those. let's actually move into the second section of this, or third section, I should say, and we're going to take a look at the equilibrium constant as well, because we just did the Q. Let's take a look at the constant when we're at equilibrium. Negative, G needs to be negative, and the K value does need to be greater than 1. And so my energy must be a positive there, okay? So these are going to be related, and so we find my delta G equals the negative RT natural log of K, okay? This must be at standard conditions. So we use those tables to calculate the spontaneity of things, okay? And so let's take a look and let's do this for my lead chloride, okay, at equilibrium. All right, so once again, now we were doing it just as it was reacting. Let's take a look at it now at equilibrium. My PbCl2, that's a solid. And so when it's at equilibrium, I'm going to get my aqueous and my two chlorides that are aqueous as well. Okay, now my equation is my delta G is going to be the negative RT natural log of K now, okay? And so we want to calculate that out. And so remember that my delta G of the reaction is going to be the summation of my G of my products minus the delta G of my reactants. We've been doing this all along, haven't we? And so to keep track of everything, let's take a look at my delta G of the reaction as a whole. That's going to be the delta G of the formation of my lead ion plus the 2 times the delta G of my chloride ion. And that will be subtracted from the delta G of my lead chloride. Okay, so plugging in values, I see that this was a negative 24.4 plus 2 times the negative 131.2, because we had 2 there. And so I've got this minus my negative 314.2. The delta G of the entire reaction then is going to be 27.4 kilojoules. That equals 27,400 joules per mole. Okay, now I can plug that value in, can't I? Now I can plug the value in right here, and so then I'll see that I have 27,400, again, that's going to be in joules, will be equal to negative 8.314 times 298 times the natural log of K. Since we're using K, my R value has changed. Okay, so then that will give, if I multiply this all out, or divide both sides by this, I'll get negative 11.06 equals the natural log of K. I can't divide by the natural log, so I multiply by its reciprocal. Okay, that's that e to the x key again. Okay, so that's that button, second function on there, e to the x of a negative 11.06. Don't forget the negative. That will give me a K value then of 1.6 times 10 to the negative 5. Okay, that's just calculating that out. That's a small value of K, but all I had to do is figure out this and then use a different constant for my R value. And I think that's going to be enough to get you through. Congratulations, we are through Unit 12. Good luck, everybody.